saying. Whatever the mass of the Earth is, and we understand it now, that would have been the equivalent mass of water in the beginning. Okay? Then the water plasma, composed of these ionized hydrogens and oxygens, mainly hydrogen 1, and oxygen 16, 17, and 18, gaseous ions called nuclides, as I already said. They're stripped of their electrons, so they're highly charged particles, just, in this highly dense, energetic ball of plasma. And there's just a lot going on there. We don't understand why plasmas really hold together, but they do, okay? Laboratory plasma is not quite as hot as this, but they are known to be formed in laboratories at lower temperatures too. And we're talking about here the energy being estimated from the bulk modulus of the Earth. Now, that's a physical property of the Earth, the forces that hold the Earth together. So if you can convert that to energy, the equivalent amount of energy you would get, you see, would be, from that would relate to a temperature of 14 billion degrees. That would be our starting point when the water was put in the plasma state. Okay? So that's our starting point, 14 billion degrees. Collisions occur between these nuclides according to the laws of statistical mechanics, which specific nuclides fuse and form new nuclides. Now, that's a process we have to work out. We have to work out from the equations, from the physics, okay, the kinetics of these processes, and keep track of everything that's going on. Keep a mass balance of all the atoms that are reacting. You say, are you never run out of the oxygen or the hydrogen? Well, if you do, there's a lot of other stuff around to create more oxygen. So there's other reactions that can take place to make up for deficiencies. But you'll never run out totally, because we separate the water that's left on the Earth as we understand it from the water that was used to make the elements. So I'm leaving out a whole lot of details here for obvious reasons. Okay? So this is a long-term process. So stable isotopes of all the chemical elements, plus the less stable radioactive elements as well, at somewhat lower temperature condition, okay, are produced, now get this, 45.2 hours. The whole scheme of chemical elements did not take billions of years. According to this, it took us, keeping record of the time process, 45.2 hours. Actually, it's less than that. So I'm being a little bit on the long side so that I don't, go too far. So it really turns out to be less than that. But it's less than 2 days. Oh, we got one more day to go before we get plants, right? Great. Okay. Evolution model requires billions of years. Well, we know that's out of the picture right now. Okay. A valid scientific mechanism for rapid cooling is workable within 20 hours of the Earth. If you start with the initial plasma and you can look at the right thermodynamic equations, and you can get the cooling processes taking place to the current state of the Earth. I'm talking about ambient surface temperature, okay? Ambient crust temperature within 20 hours, or less than 20 hours, really. Less than 20 hours. So that hot plasma is going to cool off very rapidly. Now listen, with radioactive decay, get this. In the very hot energy conditions, the decay process will be greatly accelerated. They will be annihilated almost instantaneously in seconds. So a 4.5 billion year half-life becomes seconds in that very high condition. But as it cools off in this period, it only has to drop from, say 10 billion degrees to maybe less than a billion, a little bit less than a billion degrees, and you've already got the half-life of an isotope, say like uranium, being extended to 4 billion years in that short period of time. Now, that's another story. That's another piece of work, but it's implicit here too. Okay, and that was another project that has been completed. Now, minimum of 7 hours is available for plants to be produced in a friendly environment. Everything's cool. You got 7 hours left for the day 3 to be completed, right? Okay? So don't worry about the heat. There's no more heat there to destroy plant life. So the key is what? Very high temperature initially, being sustained during the nuclear collisions. That's where the process takes place to form the elements. And a very rapid cooling process after that to bring it to ambient conditions. Well, here's the first one. Take a hydrogen 1, add a neutron to it, you'll get hydrogen 2. See that? See the blue one? Coming from hydrogen 1 neutron? There it is in the periodic table. Now, most of it is hydrogen 1, and there's some hydrogen 2 there too. But the reason why I'm using hydrogen 2 is because we're going to use it in the next reaction. Hydrogen 2 will react with the oxygen 16 that's already there, and it will produce nitrogen 14 and helium 4. So 2 more elements. Helium is over there on the right, that gray one, and nitrogen 14 is this other gray one, one row below it. Okay? Now the hydrogen 2 reacts with oxygen 17 and forms another isotope of nitrogen 15, 2 major isotopes of nitrogen, and more helium. There it is. Hydrogen 2 and oxygen 16 produces carbon and lithium. Lithium 6, carbon 12. Okay, there they are. Carbon is right on the side of nitrogen. Lithium is over on this left side below hydrogen, the yellow one. Then another lithium is produced with hydrogen 2 and oxygen 17, getting more carbon 12 and lithium 7. So now you got the 2 isotopes of lithium. You got the 2 isotopes of hydrogen, the 2 major isotopes of hydrogen. You got all the existing isotopes of oxygen to begin with from the water. Okay? Now you created the 2 isotopes of nitrogen, 14 and 15. You created the isotope of helium, 4. You created nitrogen, carbon 12 and 2 isotopes of lithium, 6 and 7. Okay, so we're building up the periodic table. Helium 4 combines with oxygen 16. You get fluorine 19 and hydrogen. Fluorine is over here on the right. Okay, right next to oxygen. That blank spot by nitrogen is where oxygen should be. Then, if we take the carbon and start reacting carbon with oxygen, we can get neon. Neon 20, 21, and 22. 3 isotopes of neon that are known. Okay? This beryllium 8 is unstable. It flies apart into helium atoms. So that's not going to create that beryllium that's in the periodic table, but it's going to allude to it because another reaction is going to create the stable beryllium in another step. Lithium 6 and oxygen produces boron. That's right next to carbon. Boron 10 and 11. 2 isotopes that are known. Okay? And then we're going to get that beryllium coming up eventually. The boron then will react with the oxygen to give carbon 13. That's the other isotope of stable carbon. Carbon 14 is radioactive and unstable.